Okay. Nice to see that some of you guys survived the homework. That's fantastic. As a reminder, your homework is due at 8 p.m. today. Just for me, maybe submit it at like 7:59. Just like maybe your computer clock is a little off from the one on Canvas. But if Canvas decides your homework is late, then your homework is late. That's the rules around here. So if you're unsure, like just a couple minutes early, because Leticia and Mark and I don't really want to get the usual emails. That said, your homework's due, I see, a late day system. So if you submit after that 8 p.m. mark, then you just lose one of your late days. Yes, Leticia. Yeah, to repeat that so that the people in the recording here, if you are a listener for this course, you are not invited to submit your homework. Like, we don't pay our TAs for that. So sadly, you're on your own. If office hours are quiet, you can come by the office hours and talk to us to go through it. But the priority needs to go to the students that are actually taking the course. Thanks, Leticia. The exciting thing about this class is the work never ends. So at the end of today's lecture, I think we even have like a fun, like timed release, like kind of situation here. So at 12:30 p.m., p.m., your homework 2 will be released. Here's the deal with homework 2. I wrote most of it, which probably means that A, the problems are like a little less ambiguous, but B, they're probably kind of tricky. So I would strongly encourage you guys to get started early, even if that means reading ahead a little bit. In particular, what homework 2 is going to do is I took one of the well-known papers in the computer graphics world. This is this algorithm called as rigid as possible deformation, ARAP, which I think actually shows up in a few classes here at MIT. Wojciech Matusik teaches a very different version of that algorithm. But in this class, we basically start with the optimization problem that shows up in the ARAP problem, and go all the way from that to an algorithm, which is basically a nice application of all of the things that we will have done and will do. So there's a least squares problem, there's an SVD in there, there's some QR, I think. So it's got all the moving parts that we know and love boiled into one big algorithm. And it's kind of cool because at the end of the day, you're going to code up a method that actually gets used in the computer graphics community. So my strong suggestion would be at 12:31 p.m. when the assignment is available, download the starter code and make sure that it runs on your computer. Computer graphics code is famously annoying to get running on everybody's machines because everybody's graphics card's a little different, all that kind of stuff. We're using this library called Polyscope, which was released a couple years ago and does a pretty good job in Python of like visualizing 3D data consistently across computers, but every year there's some challenge. So essentially, the last homework was pretty theoretical in nature. I don't think there was any coding really, but this one actually has a coding component. And moreover, the starter code does, use a little bit of your computer's resources. So get an early start. Make sure at the very least you run the starter code. And I think some of the problems on the homework you can already do. So a few of them are just like linear algebra review. So I'd encourage you to get started. By the way, as with most topics in a numerical analysis class, you can absolutely Google it and you'll probably find all kinds of implementations of ARAP. Go for it if you want to cheat, because the reality is that the way I wrote the problem doesn't really align to the reference implementation you'll find online. Okay, I wouldn't suggest going about problems that way. Instead, my preferred algorithm is like thinking. Any questions, comments, concerns? Like cool recipes, interesting New York Times articles. No, okay. All right. Well, in that case, we will get started with our lecture for today, which shockingly involves numerical linear algebra. So let me convince my laptop to show me what I want. Incidentally, we're surprisingly slightly above schedule, probably because I keep rushing and leaving topics out of lecture because I'm nervous that we're going to fall off of schedule. So we may end a few minutes early today. I say that, and now that I've said that, I'm sure we'll spill over past the end of class. But to recap our story so far, we've talked about sort of two topics so far in 67350, right? We started with the course by talking about double precision floating point and conditioning and error and stability and all that good stuff. And then we kind of like turned that part of our brains off and we talked about algorithms for solving linear systems like Gaussian elimination, LU factorization, and then in the last lecture, Cholesky. But if you notice, I did a bit of a sleight of hand, right? That essentially, the first couple of lectures, we were very concerned with like floating point and rounding and all that stuff. And then when we derived Cholesky factorization, for example, in our previous lecture, I kind of treated all the variables as like infinite precision double arithmetic, right? We didn't talk about bounding the error in those techniques. Now, you really can work out error bounds for all the different algorithms we've done so far. Those proofs are really clunky. If you look at like an old school numerical methods book in the math department, you'll find many such bounds. In this class, I think a conceit that most computer scientists are kind of okay with is like, you know, for 85% of what we want to do, probably precision is okay and we don't have to worry about it. However, it is worth talking a bit about conditioning for linear systems of equations, A, because they're everywhere, and B, because what we're going to find as we move farther along in this course is that our algorithms are going to become more and more approximate. And when I say approximate, I don't just mean double precision floating point. I mean that the actual algorithm isn't guaranteed to give me the actual solution to ax equals b, even in infinite precision arithmetic. It just gives me somewhere close, right? And so for those kinds of problems, this kind of conditioning discussion really, really matters, right? Because again, as a bit of a review of what we've done so far in this course, remember that there's this sort of difference between the error that we care about and the error we can measure, right? So for linear system of equation, right, we're trying to find x for ax equals b. What we can measure is the residual, right? We can measure ax minus b and see how close to 0 that is. But that's sort of an indirect indicator of the error that we really care about, which is the error in x, right? And so what we're going to talk about today is how to bound the relationship between those two things. In other words, if I run some numerical method for solving a linear system of equations, whether it's Gaussian elimination like we talked about so far, or, for example, conjugate gradient method, gradient descent, I don't know, what are some other ones out there, like assorted eigenvalue, Rayleigh-Ritz methods? Like there's like no shortage of linear system solvers out there. And we get some solution that doesn't actually have a 0 residual. How much can we trust it, right? That's essentially what we're after today. Notice that that question is a little bit orthogonal to the algorithm itself, right? You give me an x and you tell me, whatever algorithm I ran, I'm pretty sure this is a good solution to my problem. And now I'm trying to understand like whether I can trust you or not. Okay. So that's our question for today. Essentially, like, I think another way to pose it that's in the context of what we've done so far, gosh, this thing is a menace, is that Gaussian elimination works in theory, but of course we really implement this thing in floating point precision, so we like happily go through all those for loops, we go through the motions of doing Gaussian elimination, but as we're doing all these arithmetic operations, there's like rounding and other stuff that could be happening, so at the end of the day, I get some x naught solution, which is not actually the solution of ax minus b, but satisfies this interesting relationship that it's like, if you take the norm of the residual, probably somewhere between 0 and much less than 1, right? This is our sort of placeholder for a small number. By the way, the fact that it's a small number is going to matter here. So one thing that we're not going to do in this class is talk about what people in mathematics call large deviations, which involve like, you know, I tried to solve ax minus b and the residual I got was like 50 feet long and like really bad, right? And then you're asking a very different question in that universe, like, is there any world where I can trust even some small part of my solution? Here we are going to make the assumption that like our algorithm tried. And in particular, like it did get something where the residual was in a regime where things like Taylor series arguments are going to be okay, right? This is actually not a huge deal for linear systems of equations. I think many of our bounds still hold in the kind of slightly larger regime. When we talk about eigenvalue problems, then it really matters. Yeah, we'll come back to that later. Okay. Any questions about our sort of high-level story? I think hopefully it's pretty reasonable. And again, this is going to follow the same arc in this class over and over again. We introduce a numerical problem. We talk about whether it's solvable at all. Once we do that, we talk about a bunch of applications. Like, I could solve this thing. I could reduce these 10 different things to this one numerical problem. Then we talk about a few different ways we might solve it that are representative. Probably there's faster methods out there. And then we conclude with, now that we got a solution, it's an approximation. How good is that approximation and can we trust it? So we're going to keep following the same arc here. Okay. So let's have a little bit of review. Philippe's class right before us apparently is already preparing for a midterm, so maybe we'll call this midterm review, which is shocking to me. It's like week 3, right? But in any event, remember that essentially when we talk about error, there's sort of 2 different notions of error at a very high level that we have to worry about, right? There's forward error and backward error. The definition of backward error, I think, is the one that's a little squishier, right? But usually the way that it's phrased is that backward error is the amount that a statement of a problem would have to change to realize a given approximation of its solution. We went through these 2 examples before in class, but just as a bit of a recall, let's say that I'm solving ax equals b. I'm making linear systems. We have two different notions of error. I'm going to glance at my notes to make sure that we agree. Yeah. Okay, so let's say that x star is the true solution. So in other words, we actually have the relationship ax star equals b, and x naught is the computed solution, right? At the end of the day, the error that we actually care about is whether x naught is a good approximation of x star, right? And so a very typical thing we might do is just measure error as x naught minus x star. But as we talked about many times in this class already, we really can't compute this number, because if we could, then we might as well add the difference to x naught and get a better solution to our problem, right? So instead, we measure a proxy for error, which we'll call backward error, which in this case is a x naught minus b. Notice that b, by the way, is a x star. Oops. Oh no, I reflexively wrote that too, but today we're going to try multiple norms. And essentially the idea is this is the thing we can measure, and the question we're going to try and answer is, when is this number a good stand-in for that one, right? So in other words, if I measure the residual and it's small, can I be confident I solve my system? And what we're going to see is that it's related to properties of the matrix A. In fact, kind of surprisingly, in our proof today, we're going to see it is not related to B. This is not obvious a priori. Okay. By the way, if you write a more detailed bound, I see like a suspicious set of eyebrows in front of me. More detailed bounds will include B for obvious reasons. But the sort of standard one that people prove actually, like to first order, it turns out not to matter. Okay. So what we are going to assume when we write our proof, and this is the standard thing to assume, is that this number is small. So in other words, like, if the residual is really gigantic, then I think the right thing for your numerical software to output is like, sorry, you sucked at solving linear systems, right? Like, we can be pretty sure if you don't even have like a zero residual that like you really did a bad job of solving ax equals b. So what we're going to assume is that we're in the regime where this number is like on the order of like some small increment away from zero, okay? And because of that, what we're going to do is basically apply some kind of Taylor series argument, right? So the basic idea here is that there's two things we're trying to relate. Do you see that? Remember, in the definition of backward error, right, what does backward error says? It says that like it has to do with changes in the problem statement. So what is the problem statement for a linear system? It's basically the A and the B, right? So essentially what we're trying to relate are perturbations of A and B to perturbations of X. You guys see that? And notice that X here is a function of A and B, right? That's the way we're going to think about it today, is as I adjust A and B in my problem, X has to kind of adjust in response to that to maintain the relationship on the board. Okay. So I think I've repeated myself enough times, so hopefully you guys get the high-level story here. Now, one thing that we can do in this class is actually think a little bit about what do we mean by small. I mean, so far I've kind of used this word in a bit of a fudge-style notion. I know a lot of you guys are uncomfortable with that on the homework. By the way, numerical methods I think is totally reasonable. A lot of people talk about these methods like, yeah, that thing's pretty small, this thing's not so small, you know. The reality is it's a good skill to develop. But for today, we are going to try and be a little bit more formal about that, right? Essentially, what we're worried about is like, we want our statements to be true for like small dx, dA, and dB, right? Because outside of that regime, we're not really worried about applying the bounds that we're talking about today. And so like I sort of rushed through at the end of lecture, the reality is that when we talk about small, we mean with respect to some vector norm, okay? A vector norm is a function, you've probably seen this in some class or another, that inputs a vector and outputs some notion of its length, right? So the one that we're all used to is the 2 norm of a vector, which is like the square root of the sum of the squares of its elements. But that's one of many vector norms, right? So vector norms essentially are anything that satisfy these 3 kind of axioms here, namely that the length of a vector is 0 exactly when the vector is equal to 0. It'd be awfully weird if like you had a non-zero vector and it had a 0 length. Another one is if I scale my vector, then that's sort of the same thing as scaling its length. And the third one, which is maybe the one that like, I don't want to say it's debatable. I think over the last 300 years, we decided it really isn't, is this thing called the triangle inequality, which is basically like saying, you know, traveling from A to B is always like less expensive than traveling from A to C to B, okay? So any function that takes a vector and maps it to its length that satisfies these three things, we're going to call a norm, right? But I think the thing that I want to be careful about today is that there are many norms out there. The one that we're used to from linear algebra class is the 2 norm, which is the square root of the sum of the squares, or the square root of your dot product with yourself, if you like. That's perfectly fine. But there's many others. For example, we can generalize the p norm ever so slightly by taking any p greater than or equal to 1 and taking the pth root of the sum of the pth powers of your elements of your vector. This is the p norm of your vector for p equals to 1. This is often called the taxicab or Manhattan norm. Anybody know why that has that name? I'm guessing many people have seen it before. Yeah. That's right. So like, you know, Boston is a weird, messed up city, but Manhattan is roughly like, here's my map of Manhattan. You know, like there's Times Square. You can tell because it's a square. And like, if I want to travel on a taxi cab from like A to B, I can't just follow this path, right, which is what the L2 norm would measure. Instead, I have to move along streets in Manhattan. The kind of weird thing about the taxi cab norm is that there's many paths that are non-unique, right? And all of them have the same length. Now, I think if you're actually from Manhattan, you would totally disagree with this because, of course, traffic is like wild in the city. But that's the sort of basic model. It's oftentimes we call that the L1 norm. Okay. Incidentally, so p equals 1 is one extreme. I can also take a limit as p goes off to infinity. I'm going to have to kind of normalize when I do that. But let's think about what that does to a vector. So let's say that I have a big list of numbers that are all positive because they're taking their absolute value. And I now take them to the pth power, right, where p is really, really large. Notice that like the biggest number in that list is going to get exponentiated way more than everything else, right? So as p goes off to infinity, up to a scaling constant, we get a special norm, which is called the infinity norm, which is just the max of the absolute value of any element in my array. Okay. Exercise left to the reader. Every single norm I've given you so far satisfies the triangle inequality and all those other axioms. I don't think we're going to go through that here. That's more of like a college analysis kind of thing to do. All right. Any questions about definition of a norm? Yeah, I think this is stuff that we've probably seen or can at least kind of vibe with a little bit. By the way, I think a nice visualization that you'll see a lot, especially in advanced classes and optimization, that I think is worth knowing, is to visualize the unit circle in different norm. So in general, you know, actually there was a really terrible, speaking of the New York Times, there's this terrible like math quiz in the New York Times a couple weeks ago where they like showed these like, they showed actually exactly this picture and they're like, which of these is the unit circle? And then you're supposed to say like all of them. And then, but the really like, as a mathematician, I kind of read it and thought like, well, that's really debatable. But at least in analysis, one of many ways to define a circle, other than like the locus of points that are, you know, like cosine and sine or whatever, would be the following. The circle with respect to a given norm is the set of x with the property that the norm of x is equal to 1, right? Now, in general, the like round circle that we all know and love, you know, the Vitruvian man situation, is for the 2 norm. But as I adjust p around, I get different unit circles, right? So for example, for p equals 1, we get this picture on the left-hand side. And like, initially this feels a little bit mystical, but it actually makes sense. So like in the upper quadrant, right, the coordinates are positive, so I don't need to worry about absolute value. So this is like this set of points that are satisfy x plus y equals 1, right, which makes this diagonal line. That makes sense? Now, why is that going to be important? So you could imagine a universe where conditioning of your problem depended on what norm you chose, right? Like maybe my problem is well conditioned in the 2 norm and poorly conditioned in the infinity norm or something like that. Spoiler alert, that actually really can't happen, at least for linear systems. We'll talk about that in just a moment. The other reason to know that is that like different norms are going to be useful for different circumstances. So to give you kind of a fun example, since we have a little bit of time, remember that last lecture and on your homework we talked about this idea of Tikhonov regularization? So the basic idea there is I want to solve some least squares problem. So I think the standard there is to use the 2 norm. That's also debatable, but let's say we leave that for now. One thing that you could do is say, like, let's say the system is underdetermined or poorly conditioned or whatever, then I might add a regularizer. I might add alpha times the norm of x. Now, the standard choice, mostly because it leads to an easy numerical problem, is to put the 2 norm there. But one thing that you might do is substitute other norms. So for example, a very standard one that I think you see in a lot in advanced courses in this department is to put the L1 norm here. Anybody have any idea why? Yes? Yeah, it promotes sparsity. Now my next question is, why does it promote sparsity? Yeah, see, I'm giving you a hard time, but reality is I think that that's sort of the mythology we see a lot in computer science, but we don't think about it too critically. But actually, this picture can really help you understand that. So let's see how. So let's say that alpha here, as always, sort of satisfies the condition that 0 is less than alpha is like way less than 1. So in some sense, what's going on in this case is that really I'm looking at all the x for which ax equals b and trying to choose the one with the smallest L1 norm, at least kind of approximately. Okay, so let's draw a picture of what that looks like. So we're going to do the simplest case where x only has 2 components in the plane. Okay, and let's say that A only has 1 row, in fact. So this is a really, really simple case. So in that case, the set of points where ax equals b is just like a straight line. Do you guys see that? So what are we doing in this case? Like in some sense, we're trying to choose the point on this line that has the smallest norm of some sort, right? So one kind of animation you could keep in mind is that you sort of make advancing unit balls, or not unit balls anymore, balls of radius r, until that ball just touches that line, and then the intersection of those two things is roughly the solution to this problem. Yeah? Okay, so if I do that with L2 norm, what's going to happen? I draw a bunch of circles. Eventually, I get this point here. Yeah? Notice that this is not sparse in any sense. It's just like 2 numbers somewhere in the plane. Now, let's think about it with this, this picture we have on the screen here. So here's my same picture. And now I'm going to draw unit balls in the L1 norm. I'm sorry, shockingly, your instructor is not an artist. Do you see what happened? The intersection here happens to be right on the y-axis. That's not a mistake. Essentially, the unit ball in the L1 norm is really pointy. And it's pointy exactly at the places that are sparse on the axes here. And so I think this is a perfectly reasonable pictorial way to understand why L1 regularization is so popular in computer science. Is A, it's almost everywhere differentiable. B, it's convex, so it doesn't like have some weird shape like this. It's actually a norm. And C, it still promotes sparsity because at the end of the day, the corners of that simplex have a bunch of zeros in them. Yes? For overdetermined system. Yeah, that's a good question. I mean, I think generically you can think of this thing as living on some plane or some quadratic form. So the same picture kind of still works out. But I'm not a good artist, so we'll skip that for now. It's a good question, though. Yeah. I think, by the way, there's another really cool explanation of this that I really love from Daniela Witten. She's a statistics professor at Hopkins, I believe. And the way that she explained it was as follows. It's sort of like the reverse of this picture. Let's say that you see a bunch of kids running around a dining room table, right? And somebody stubs their toe. Almost inevitably, where do you stub your toe? On the corner. That's right. And so somehow there's like this interaction between the L2 norm and the L1 norm is the thing that's creating sparsity. You tend to run right into the points of the simplex, which are exactly the corners of this object here. Okay. So in any event, hopefully you guys get the point that as we measure length, the notion of length actually really matters. And by the way, it's not just like a fun thing we get to choose. It really is paired with applications. So to give you an example, let's say that I have 2 vectors, 100, 0, and 100, 100. So notice in L2 norm, like the norm we're used to thinking about, these 2 things are very vastly different, right? Obviously, the second one has much bigger length than the first. But in the L infinity norm, these actually are the same length, right? So in some applications, like if I want to bound the maximum error of my problem, maybe L infinity makes sense. In other ones, if I want some more like root square style notion of error, then maybe L2 does. So this is not just an abstract mathematical choice. It really does have to do with what kind of error you care about. Cool. All right. The good or bad news is as follows. There's a lemma. I think it's proven in the textbook. I should know. I wrote it. But we're not going to have time to prove it in class because it involves a little bit more machinery than the prerequisites of this class, which is as follows. We can define a notion of two norms being equivalent, which is given on the screen here. Hopefully this makes sense. So essentially, two different norms are going to be equivalent to one another if you can come up with two constants that kind of sandwich one norm between the other two. Okay? Now, by the way, I think in some textbooks, they just take one of the constants to be like 1 divided by the other constant. Hopefully you guys can see that doesn't really matter. I don't like that definition because somehow the units are weird. But in any event, okay, so two norms are, sorry, I keep saying two norms. I mean like two different norms, not the two norm, are equivalent to one another if essentially they can be sandwiched. And notice especially as the norm goes to 0, sort of what you're saying is that like, you know, you can draw, I feel like there's this usual kind of mathematical picture where you draw this little like, you know, set of sandwiches, and then your other norm is kind of squished in between the two. Obviously, this isn't the right picture because it went negative, but there's some version of this that's similar. The basic idea being that like as your length goes to 0 in one of these norms, you can't be in a situation where it like flies off to some other number in the other one, something like that. Now, this is just a definition of equivalence. And there's a really interesting result out there, which is the following. Actually, every single norm on Euclidean space is equivalent to every other one. This is actually not entirely obvious from the definition of the norm. It's a fun exercise if you want to prove it. Here's my basic outline of how you do that. One thing that you can argue is that a norm is a continuous function. You can't like have a jump in the norm of a vector if you take a sequence of vectors that approach one another. And now what you can do is look at the norm as a function on the unit ball, like on that object that we defined a few slides ago. That's a compact set for the mathematicians in the room, which means in particular, there is some point on that ball where it achieves its maximum and some point where it achieves its minimum. And then you can use those points to essentially derive the constant C low and C high. So I'll let you think about that. Okay. And again, even though they're equivalent, I want to be 1,000% clear that like in reality, these constants can be really, really chonky. And so away from 0, you can end up in this situation like what we've already written on the board, where they're vastly different and measure very intuitively different aspects about a vector. Okay? All right. Now, we're going to need one additional thing when we talk about our error bound. Yes?
I'm struggling with the intuition of what it means for two norms to be equivalent while behaving very differently.
Essentially, the constant C here can be very large or very small, right? That's all. Right, and notice that only really matters as x gets to be like tiny. Yeah. Okay. The other thing that we're going to need in our construction of a condition number for linear systems is a way to measure the norm not only of a vector, but also of a matrix. Remember that we're talking about solving ax equals b and like perturbations in a and b, right? So we need a way to not only measure lengths of vectors like b, but also to measure some notion of length for a matrix. Yeah? This is something we call a matrix norm. And it's basically satisfies all the same axioms, right? The definition of a matrix norm is exactly the same as definition of a vector norm. But now the question is like, what notion of norm should we choose for matrices? Now there's a standard choice. I think, especially these days, everybody's so used to Tikhonov regularization in different forms in machine learning you don't even think about. There's something called the Frobenius norm. If I recall, Frobenius is one of these interesting like 19th century mathematician names that they just like for some reason lift a Latin last name. For like a German guy or something. But in any event, the Frobenius norm basically says, I'm going to pretend like my matrix is secretly a vector. Like I just kind of unroll it into one long list of n squared numbers, and then take the 2 norm of that vector, right? That's a perfectly reasonable matrix norm in the sense that it like very clearly satisfies all the axioms that we want. Now, something I think we don't think critically about, what does a Frobenius norm actually measure about a matrix? It's like not entirely obvious from the definition. Do you see that? That like in particular, when you talk about like the 2 norm of a vector, it's its length. It's an easy thing to draw a picture of. If you think of a matrix as like a linear map, like a thing that inputs a vector and outputs a vector by virtue of matrix multiplication, I see you. Then it's really not clear what the Frobenius norm measures in that sense. You can come up with that. It has to do with the singular values. But from this definition, it's a little bit unnatural. It's almost like we just lifted something that really made sense for vectors and just dropped it on the entries of a matrix, right? And so when we talk about matrix norms, the thing I want to point out is that, in particular, this matrix norm has very little to do with the action of A on a vector. And so maybe it makes sense, obviously, because I'm asking the question, to derive other norms that act on matrices in a more intuitive fashion. Question? Yeah. So in particular, there's a definition of a matrix norm which is directly related to a vector norm. Essentially, for every single vector norm out there, I can define a norm of a matrix which directly has to do with the norm of the vector that I defined. That sentence was poorly phrased, but that's okay. Which is as follows. So essentially, let's say that I have this double bar here is a norm on a vector, right? Then one thing I can do is I can look at the unit ball in my space. So let's draw maybe the L2 version of the picture, because I think that's the one that all of you guys are probably used to. So let's say that I look at the unit ball in the L2 norm, which is a fancy word for circle. Actually, apparently all of those pictures are circles, according to New York Times. Okay, and I look at the image of this circle under a linear map. I feel like all of you have probably drawn some version of this picture like 8,000 times in linear algebra class. And of course, this gives me some deformed circle, otherwise known as an ellipse, right? And so the definition of the induced matrix norm corresponding to the 2 norm of a vector is the point on this object which is farthest away from the origin, the length of that. Okay? And you can do the same thing for all the other norms, right? I mean, you could also do this for L1 norm. The picture is a little bit funky. I think you get like a, some kind of, some pointy guy like that. Whatever, it's not gonna, don't pay too much attention to this picture. Essentially, in each of these cases, I think the geometric picture here is pretty straightforward. You take the unit ball, you map it forward under your matrix, and then the definition of the induced norm of the matrix is the biggest length of a vector you can get under that map. Does this definition make sense? Something that I'll let you guys check at home is that this thing satisfies the triangle inequality. It's very clearly positive and scales the right way. And the triangle inequality is basically a byproduct of triangle inequality for vectors. Okay. Now, the nice thing about this norm is it clearly knows something about the norm of the vector that we've chosen. And that's going to be kind of important because essentially, to remember the goal of our lecture here, we're trying to ask the question of if I perturb A and B, how does X change, right? And notice that we need to talk about perturbations of A, B, and X all in the same language. So we need to give them kind of the same operating system to talk to one another. And using the induced norm is going to help us do that. Okay? Cool. Okay, fun question for the day. We could ask, what is the matrix norm induced by the 2 norm of a vector? For fun, let's actually do that calculation. If we have time at the end of the lecture, we'll go back and talk about the induced norm for the infinity norm of a vector, but I'm a little nervous to get to the end of the calculation I actually care about. Okay, so let's say that I want to know this quantity. By the way, when you do your homeworks on like matrix norms, you better remember to put that subscript there if it's needed. Okay? So secretly, this thing is an optimization problem, right? What is it saying? It's saying maximize over all x the norm of ax 2 subject to the constraint that the norm of x is equal to 1. Right? So the optimal value of this optimization problem is the definition of the matrix 2 norm. Cool? All right, so we have an optimization problem staring us in the face. So probably what we should do is take the derivative, set it equal to 0, all that good stuff. Sadly for us, there's a constraint. So we need to dredge up some other annoying thing from linear algebra class, or from multivariable calculus class that we haven't yet used in this class, but we will today. Anybody remember what it's called? Lagrange multipliers. That's right. So I'm going to write the Lagrangian of this problem. By the way, chapter 1 of the book, if you don't remember how to do this kind of thing, goes through some examples. So in particular, the Lagrangian of this problem is a function of x and of a Lagrange multiplier lambda. And it's going to be the objective function plus lambda times the constraint. Like that. Cool? And now I take the derivative with respect to x, with respect to lambda, and then I get some relationship that glues all these things together. Hopefully this story kind of sounds familiar from calculus class. It's okay if you don't remember this one, like you should go at home and review Lagrange multipliers and look back at this proof because it's a good one to review. Okay, by the way, for convenience, obviously minimizing ax is the same thing as minimizing 1/2 ax squared. And similarly, I can do the same thing for the norm here. And in fact, I can even scale lambda just for fun. This is just called lazy mathematician behavior. All these constants don't really matter. Okay, so now let's differentiate this with respect to x. What am I going to get? I'm going to get 0 equals A transpose AX. Oh boy, that matrix looks familiar, huh? Minus lambda x. Now you can see why I put all the 1/2 there, just because I'm lazy. Okay, so in other words, what did we show? We showed A transpose AX equals lambda x. So in other words, somebody help me out. Ah, come on, you guys, you're always answering questions. Somebody else. You also answering questions. Like somebody other than like the same 3 people. Yes. Yeah, this is the definition of eigenvalues. This is the first time we've seen eigenvalues in this class. Get excited because they're about to happen a lot. Okay? So, what did we show? We showed that this unknown lambda, which we kind of just invented, is at least an eigenvalue of A, and that x is the corresponding eigenvector. Remember that at the end of the day, the quantity we actually wanted was the norm of AX, which is, of course, the same as the square root of the norm of AX squared. Like that. Yeah. Okay, so AX is equal to lambda x, right? So, oops, wait a second. Oh, yeah, this is me. Okay. So in other words, we have this relationship. By the way, remember this matrix is positive definite, so we know that lambda is greater than or equal to 0. Okay. What is this quantity? Well, by definition, x has length 1, right? So this is just square root of lambda. Okay. So there's one thing remains. We haven't said which eigenvalue. Yeah. But remember that we have a maximization problem. So what we can conclude is that the 2 norm of a matrix is equal to the square root of the maximum eigenvalue of A transpose A. In a couple weeks, we're going to see that that is the same as the maximum singular value of A, but we don't know that yet in this class. Cool? Notice this is also going to create a little bit of an annoyance. So we're about to derive a condition number formula in terms of these norms. You see what's going to happen, which is pretty irritating? Our condition number is going to involve this quantity, and we don't actually have any algorithms for computing it. And in fact, they're probably harder than solving linear systems. So the worst thing that the best thing we're going to be able to do is just bound things. Hamid, you look like you're dying. What can I do to help you out? No, because this thing is square root of x transpose AX. You agree with me there? And lambda is an eigenvalue of this matrix. Yeah, almost got me. Any other questions? Fabulous. So on the screen here, I'll give you some formulas for other induced norms, the one norm and the infinity norm. Remind me if we have time at the end of lecture, and we'll derive the formula for the infinity norm of A. It's just a simple argument. Notice the nice thing about these 2 norms is they're actually computable, right? If you're just given the entries of your matrix, these ones are pretty straightforward to work out. Sadly, what we're also going to see is for computing singular values, we're going to need the norm of A and the norm, or sorry, for computing condition numbers, we're going to need the norm of A and the norm of A inverse. And it is not obvious what the infinity norm of A inverse is going to be without calculating the inverse of a matrix. Somehow there's like a conservation law here, like there's just like some amount of annoyance that's conserved regardless of what norm we use. Okay. So quick question to check everybody's understanding. Are all matrix norms equivalent? How many of us vote no? How many of us vote yes? So there's like some secret third category that I'm missing here. Yeah. Yeah, so matrices are sort of by definition grids of numbers. Yeah, that's true. If I said linear operators, the answer would be different as a hint. Yeah, so the, yes?
Oh,
We vote for whatever that last thing was. Yeah, no, sorry, I'm giving you a hard time. So yes, the answer is absolutely. So remember that the set of matrices, you can take any matrix and unroll it to a vector of length mn, right? And so in particular, every matrix norm is also a vector norm on that particular space. It's a weird vector norm, but it's still a vector norm. Yeah, and so that argument shows all matrix norms are also equivalent to one another. Okay, so our real goal today, I've managed to kill 45 minutes before getting to it. Oh no, that's not right. Wait, we started 11:30? 11? We started 11. Oh, I'm going slow. Is to derive a condition number for solving linear systems of equations, right? Remember, that's going to be some ratio of forward to backward error. And in today's lecture, we're going to do kind of a cool thing, which is we're going to do like the grown-up condition number, where our errors are measured relative. So we're going to do like divide by the length of the vector. College textbooks usually don't do this. They do the kind of weird version of error that has some units to it. But our units are a percentage, which is nice because then they don't depend on the scale of A and B. Okay, so in particular, here is the model problem we need to solve, which is we're going to have x, which notice that epsilon equals 0, x satisfies our linear system of equations, ax equals b. And now what we're going to do is we're going to start taking our matrix A and our vector B, and we're going to perturb it ever so slightly, right? We're going to adjust A by adding a little multiple of some other matrix delta A. And similarly, we're going to take B, and we're going to add some small annoyance delta B. And our question that we're going to try to answer is, how does x change in response to these things? In numerical methods, often we call this sensitivity analysis. Yes? Yes, x is absolutely a function of epsilon. Let's think about it. So as I adjust epsilon, the linear system that x satisfies basically changes, right? So in order to maintain that relationship, x has to change. No problem. Yes?
What is epsilon?
Epsilon is a number. In this case, it's just like the amount that I perturb in this direction A. So you should think of it as like a small number.
I see.
Yeah. In general, in this class, I'm going to try to be consistent that epsilon here is usually a stand-in for something small. Yeah. Great questions. Sorry, I'm giving everybody a hard time today. I didn't have enough coffee. Yes, Hamid.
What is delta A?
It's a matrix. No. So the idea here is that like there's a universe where like if I perturb A in one direction, then my system doesn't change. If I perturb it in some other one, it does, right? And so for now, we're just going to leave it all up in the air. We're going to say somehow delta A is kind of like maybe the difference between A and the floating point version of A, and similarly for B. And now we want to know like roughly how does X change in response? Yeah. So we don't know anything about delta A or delta B. We're putting no assumptions on them so far. And what we're going to see is that we can come up with some nice bounds that help us understand that. Yeah, one more question.
Is it enough to just add like the small change that reflects the thing?
Come again?
Like, is it just enough to add a plus the small change, or like
I'm not sure to understand your question.
like you're trying to change the x as a function of the small number?
Mm-hmm.
Is it enough to just change a and b by like addition operations that satisfy x small change?
So I don't think we have so basically this is sort of an overdetermined problem that like, if I know epsilon, delta A, B, and delta B, I know X. I don't have a choice. Do you see that? Because assuming that the matrix on the left is invertible, right? Basically, I can define a function x of epsilon, which is equal to A plus epsilon delta A inverse times B plus epsilon delta B. This is, ooh, dyslexia is tricky. But in any event, this is a function. Do you see that? It maps an epsilon to some vector. Yeah. I've decided to write this implicit relationship because we don't really know how to differentiate through this object. Yes?
If we're treating delta A to be some small perturbation to A,
Mm-hmm.
and we're treating delta B to be some small perturbation to B, why are we multiplying it with epsilon another form?
That's a reasonable question. So like somehow this notation feels redundant. That's absolutely right. So in this case, actually, you don't need to think of delta A and delta B as small. They're just some direction. There's a different version of this proof that uses multivariable calculus where you just remove the epsilon and you differentiate in all the entries of delta A and delta B independently. We're just kind of using this as a way to bypass that. That's all. Okay. Yes?
If we're just checking perturbation, why do we need to perturb both of them?
That's a good question. So the question was, why do we need to perturb both A and B? So remember, the goal of our analysis here, right, is to basically understand how X changes in response to changes to the statement of our problem. I would argue the statement of our problem is an A comma B pair, right? So we need to account for both of those. Obviously, when we write down our final formula, if we ever get to that point, you can substitute in delta B equals 0, and you'll get the special case that you're talking about. And in fact, one thing we're going to see is the formula we derive actually doesn't depend on delta B, but that's not obvious right now. Yeah. Okay, so let's actually do the calculation, and maybe that will help give some clarity to you guys. For once, I think I actually haven't made a mistake, but somehow I've still lost half the room. Cool. Which is on me. It's not on you. You guys are great. All right, so unfortunately for us, this calculation is like mildly hairy, only mildly, but it's the kind of hairy calculation I like to do, so that's good. Like, yeah, this is the beginning of the transition of this class from algebra to calculus, which is nice for me. I'm kind of a calculus girl. All right, so what are we trying to do? We have this implicit relationship as follows. Basically, we have A plus epsilon delta A times X equals B plus epsilon delta B. Here, we're going to think of X as a function of epsilon. Is it okay if I don't keep writing the parentheses for now? Okay. So one thing that I can do is I can just differentiate this relationship implicitly, like differentiate both sides in epsilon. Yeah? Okay. Remember that there's actually two epsilons hiding on the left-hand side, so we need to apply the product rule. Yeah? So when I differentiate the left-hand side, what am I going to get? Like delta A times X plus, I guess, right, yeah, A plus epsilon delta A X prime. Hopefully I've done that right so far. And on the right-hand side, anybody want to help me out? What's the derivative of the right-hand side with respect to epsilon? Yes, delta B, that's right, because everything else is constant. Everybody see how we got from the first thing to the second here? It's just calculus. Remember that old music video with the like u plus me equals us? I know my calculus, never mind. Okay, so in particular, we're only really concerned about perturbations away from 0, right? We're like talking about small changes to our original solution, ax equals b. So it's actually sufficient for us in our argument today to substitute in epsilon equals 0. So in other words, just as we slightly perturb away from the solution of our original problem, what happens? So in that case, we're going to get delta A times x, oh no, I was going to write x0, but I realized that in the original slide, I see you, but let me finish the sentence. In our original slide, I called x0 the noisy solution to my problem. Are you guys going to be really angry at me if I use that notation to mean x at time 0? Is that okay? I'm so sorry. Okay, so x0 is going to be the thing that satisfies A, x0 equals B. Okay, just because I don't want to keep writing parentheses. Okay, so in any event, notice if epsilon is equal to 0, that thing goes away. x0 prime equals delta B. So far, this isn't so bad. Yes?
I missed what you said. So we care about the case where epsilon is small.
Yeah.
Then when you set epsilon equal to 0, like that feels like a different case than epsilon being small. You're saying it's like epsilon is 0 is separate from epsilon as a small number.
So what we're going to do is we're going to write x of epsilon equals x naught plus epsilon times question mark plus. That's really what we're doing. And this thing is x prime of 0. Yeah. Okay, any other questions? I'm glad you guys are thinking critically, but also we're a little low on time. Shockingly, I didn't expect that. It's just fine, that's good. Okay. Fantastic, so notice that this actually gives us an expression for this object, assuming A is invertible, right? I can just isolate it, and what I'll get is x naught prime is equal to A inverse times delta B minus delta A times x naught. Cool? All I did was rearrange the expression on the left. Okay. So far, we're doing pretty good. By the way, like many of you in machine learning have probably come across this document called like the matrix cookbook that has all these weird derivative formulas. Notice we accidentally just derived one of them, like the derivative of matrix inverse. I'll let you think about how to generalize this ever so slightly. But what we're really after is the error in X. Remember, that's our goal, is to bound some quantity. So in particular, today what we're going to do is we're going to try to bound the relative error of X, which I will define to be, and this is going to go to your question, X of epsilon minus X naught divided by the norm of X naught. Right? This is sort of like the definition of relative error for X as I perturb in the epsilon direction. That makes sense? I'll move my hand so you can actually read it. Okay. So if we plug in the Taylor series that I just erased, what we're going to get for the numerator, of course, oh no, I keep banging into this thing and then it loses my page, which isn't good. As this follows, this is epsilon x prime 0 plus big O of epsilon squared divided by the norm of x naught. Do you guys see that? So basically, this minus x naught got rid of the first term in the Taylor series. This is the second term in the Taylor series. And this is my fudge factor for everything else. Okay. Well, lucky for us, we actually have a formula for x naught prime, so we can now plug that in. Yep. So when we do that, we get, I'm writing kind of small, and I'm trying to say it out loud, so hopefully you guys are taking notes and like thinking critically, because this is probably hard to read from the back of the room. Incidentally, there are many seats right here. Okay, so we have this epsilon times A inverse delta B minus delta A x naught plus big O of epsilon squared. All of this divided by norm of x naught. Cool. All right, now we're going to do what everybody loves to do in analysis class, which is like triangle inequality our way out of this problem. Okay, we're actually getting pretty close to the bound that we want. So notice there's a bunch of terms here. There's like 1, 2, 3. So what we're going to do is basically apply the triangle inequality to separate all of these things out. Okay. So in particular, yeah, okay. I did this out of order from my notes, which is dangerous because that means I have to think critically in front of humans. Okay. So in particular, notice I can kind of pull an epsilon out of this expression. So I'm going to do epsilon, oops, that's just an absolute value, over the norm x naught, right? That's this annoying thing we keep carrying around. And now applying triangle inequality to the rest of this thing, I've got A inverse delta B. Okay. We've got A inverse delta A x naught. Like that. Okay. And then I can just add my fudge factor, pull that out. Everybody agree with me so far? Okay. Now we're cooking with gas, right? Like we're starting to get something that kind of looks like an error bound. It's not quite what we wanted. Like it doesn't look like relative error on the right-hand side. Like we haven't divided by the norm of A yet. I see you. But somehow we're getting close. Yes? We put out an epsilon, but notice the plus sign is outside of these parentheses. Yeah. There's mistakes. So this time I actually checked my notes twice because I was so nervous to get this calculation wrong. Okay. So now we're going to have a mild digression because we have expressions of this form, right? We have like kind of the norm of A times a vector. And remember, like what we're trying to do is to relate this to errors in A and delta and B separately. So it would be kind of nice if we could like separate out the norm of A and the norm of B here. Now, this is where we're going to use the fact that this norm we're going to choose is going to be specifically the norm that is induced by the norm we use on vectors. Okay? That's going to be the conceit that we make. And that's going to allow us to prove a handy formula. Now, how many of us remember Cauchy-Schwarz inequality? Right? So Cauchy-Schwarz inequality is kind of like, you know, the dot product of two vectors is less than less or equal to the product of their norms, at least in the L2 norm. Notice that this kind of feels like we can do something like that, but there's two problems. One is that this isn't a dot product. The other is that this isn't the 2 norm. By the way, I found at least one textbook that shall not be named that pretended like this was Cauchy-Schwarz. It's not. Okay. So I'm going to try an experiment. We're going to prove a little lemma on the the board that goes in the back, but then topologically I'm going to end up covering it up. But it's basically going to just justify that we can do the formula we want, okay? So in particular, suppose we use the induced norm of A by some vector norm, like that, okay? And that so we have some vector v, and it's not equal to 0. If it's equal to 0, then like all of our claims are kind of boring, okay? So we're going to prove 2 useful formulas. I keep erasing because I insist on not using paper for my notes. Okay. The first one is as follows. Can we come up with a norm, an upper bound on the norm of A times V, right? You can probably guess where we're going with this. We would like this to be upper bounded by the product of the matrix norm of A and the vector norm of V, okay? In order to do this, I'm going to do like one of these annoying smartass mathematician things, which is I'm going to multiply and divide by the number, like the same number, and then I'm going to kind of parenthesize things in a nice way, okay? So in particular, since we assume that V is not equal to 0, what do we know about the norm of V? Yeah, it's greater than 0. So in particular, this is equal to the norm of V times the norm of A times V divided by the norm of V. Do you see that we actually used like 2 of the different kind of axioms for norms here? Okay. So now what? Well, what happens if I take a vector and divide it by its length? You know, this is a unit vector, right? So in particular, notice that this is less than or equal to the max of this expression over all unit vectors, right? So this is less than or equal to norm of V times the max over W with norm 1 of A times W. Do we see how we got this bound? Essentially, like this is some instantiation of this expression, but we don't know it's the max. Okay? Notice this is the definition of the induced norm of A. Cool? See, not Cauchy-Schwarz inequality. We don't even need dot products here. Like we're in a universe where it might not be possible to take dot products. What do you call that? It's like Finsler geometry? No, that's the one where you things are asymmetric. I forget. Anyway, okay. The other lemma that we're going to need is as follows. It's kind of similar, which is can we upper bound the norm of the product of 2 matrices? Unsurprisingly, this is like very similar to the previous proof. Okay, what is the definition here? This is the max over all W, whose norm is equal to 1 of the norm of A, B, W, like that. Okay. What can I do? Well, notice from the previous inequality, if I parenthesize it like that, right, the norm of A times BW is less than or equal to the norm of A times the max over W of the norm of BW. Do you see that? Like essentially all I did was apply exactly this fact here. Okay? What is this quantity? This is the induced norm of B rather, yeah. Okay, so essentially we've just double checked that like we can do mathematical sleights of hand that we like probably I could have used and you guys wouldn't have questioned, but like we should be careful about it. Any question about these 2 little lemmas? Basically the norm of the product is upper bounded by the product of the norms in like all cases, vectors, matrices, whatever. Actually, the one case that we didn't show is like 2 vectors, I suppose, but that's we're not gonna worry about. Okay. Is anybody gonna be angry at me if I cover up this proof with a blackboard? Okay. I have a bad habit of doing that while I'm lecturing, and I know that it's irritating if you're taking notes. Okay. So now we're going to return back to our main story, right? We had a bunch of expressions that felt like we could bound them, but we weren't confident. We needed these little lemmas. Now that we have them, we've had our nice little detour, we can go back and finish off our proof. and derive an expression for condition numbers, which is cool. Isn't this proof fun? Like, it's somehow very elementary. Like, it's very nice that you can do this. If you're curious, I shamelessly stole it from, I think, Golub and Van Loon, which is sort of the Bible of this sort of thing. Okay. All right. So this expression, now we know, is less than or equal to, I really want to write norm of epsilon, but I know that's not right. The absolute value of epsilon divided by the norm of x naught. Okay. And now, what do we have? We have the norm of A inverse times the norm of delta B, like that. Plus, we got a bunch of terms now. The norm of A inverse times the norm of delta A times the norm x naught, like that, plus big O epsilon squared. Have I managed to make a mistake? I think we're good. Okay. So now it's just a question of reshuffling. All right. So in particular, because I happen to have a godlike ability to know what's at the end of my calculation, I'm going to factor out some terms that I know are going to make my life easier. In particular, notice that there's like an A inverse and an A inverse there, so it makes good sense to factor those guys out. And I'm going to do a sneaky thing, which is I'm also going to factor out the norm of A while I'm at it. And let me explain why. So in particular, this is equal to absolute value of epsilon over the norm of x naught. I'm going to say times the norm of A inverse. That part makes sense to factor out. Then just for fun, while I'm at it, I'm going to factor out a factor of the norm of A. For those of you who have taken the undergrad version of this class, you might recognize this quantity. It's called foreshadowing. All right, so what are we going to have here? So in particular, let's see here. We have norm of delta B, norm of A, like that. Wait a second. Did I? Yeah, that's fine. Plus, okay, so this went out. Oh, I see what I did. Okay, yeah, that's fine. Sorry, I keep departing from my notes and then getting myself confused. So we have delta A times the norm of x naught divided by the norm of A, once again, like that. Okay? Cool. All right, I'm going to do one additional thing, which is I'm going to factor out the norm of x naught. I intended to do that before, and I forgot. So in particular, notice that we've got a 1 over x naught there, and I've got an x naught here, right? So I can cancel those two guys so long as I put x naught there. Cool? I'm sweating. You can see I'm getting a little nervous. Okay, so let's step back for like 10 feet and get excited about the direction this proof is going, because I think it's exciting. Notice, what is this quantity? It's relative error. You see what happened? We started with relative error in x all the way to the beginning of this. You probably forgot by now because we've done like 20 calculations and like a few lemmas in between. But the whole point here was we're bounding relative error in x. And here, we have relative error in a. That's pretty cool. What's a little less cool is like whatever the heck this thing is. Yeah? And so, however, there's like some vibes that like make us think maybe we're moving in the right direction. What is a times x naught? B. We have the norm of A times the norm of x naught. That's not quite what we wanted. Yeah? What do you think we're going to do? We're just going to apply our lemma one more time, right? So in particular, A x naught equals B. So in particular, the norm of A naught x naught is equal to B, like that. So in other words, we have B is less than or equal to the norm of A times the norm of x naught, like that. Here we have 1 over that quantity. So all I'm going to do is take my inequality and flip it over. So in other words, I don't know, 1 over the norm of A times the norm of x naught is less than or equal to 1 over the norm of B. I lost points in a middle school algebra exam for forgetting to flip that inequality, and it really burned me about like 35 years ago. Okay, so notice now this factor and that factor are exactly, I even did you guys the courtesy of taking the reciprocal so we don't have to think through inequalities flipping backward. So notice that I can upper bound this thing by just replacing this quantity with B. Cool? Are you guys going to be annoyed with me if I just erase this and write norm of B because I don't feel like writing like this entire expression again? Is that cool? We're friends here? Okay, so I'm going to say this thing is like that. Yes. Ah, now you're annoyed. Oh, that's right. Yeah, thank you. Absolutely. Okay, this is our final result. Beautiful, right? So let's talk about it a little bit. Like, actually, this thing looks kind of ugly, and so we're going to do what all math professors do, which is just give names to all the terms in this expression, and then it looks clean because I just factored them all out. So in particular, I'm going to call this thing kappa. The K stands for condition number. I'm going to call this thing D. What is D? D is the relative error in my statement of my problem. Do you see that? So what did I show? This is really equal to epsilon times kappa times D plus big O epsilon squared. Cool? All right. So this is the really exciting fun formula. So essentially, what we did is we defined a number kappa, and I claim, or I'm gonna call this the condition number of solving linear systems of equations. And let's talk about why that's a reasonable thing. Remember that essentially condition number has to do with the ratio of forward to backward error. Notice we started with forward error all the way back up here, and we ended with backward error there. So if I divide both sides by delta, that's exactly what I got, up to this factor epsilon, but the epsilon's kind of on both sides, so that's okay. And so, right, so essentially what we showed is that this kappa is sort of bounding the relationship between error in these two universes. One is residual, and one is the error, the linear system itself. Okay? Now, let's do a few sanity checks, just for fun. Let's think about, remember that like in our previous lectures on conditioning, small condition number meant that a problem is well conditioned. So let's think through that sentence a little bit and make sure that we agree with it, okay? So in particular, let's say that kappa is small. Notice what that says. That says I can have a large amount of error in D, which is my problem statement, and X doesn't change very much, which is exactly what you would expect. Cool? All right. So essentially, yeah, that's the bound that we proved. Moreover, it's pretty easy to show that kappa is equal to 1 for the identity matrix, basically because this is A inverse and A are both going to be boring in that case. But in particular, I think one thing that's useful to do is to actually work out what kappa is for a few different matrix norms. In particular, the 2 norm, I think, is the one that everybody's used to seeing. In fact, I think most textbooks skip directly to the 2 norm formula without passing through this thing first. Okay? Any questions about our definition? Yeah. What do you do in A is not invertible? Is that a well-conditioned problem? Yeah. What's the norm of A inverse in that case? That's right. Yeah. So, and in fact, let's see that by actually plugging in the 2 norm and seeing what we get. So remember that the 2 norm of a matrix is like the largest singular value, or if you don't know what a singular value is yet, it's the largest eigenvalue of A transpose A, square rooted. Okay, so if we plug that formula in here, then essentially, oh, by the way, this works for this formula is true for any matrix norm, right? This is the definition of matrix norm on the right-hand side. There's one small thing that I've done, which is kind of pull the inverse out of the norm, which turns out to be okay. Okay, so in particular, remember at the beginning of this lecture, before we derive this ugly bound, right, we showed that essentially the norm of a matrix A is its largest singular value, or the largest eigenvalue A transpose A. One thing you can convince yourself is that the norm of A inverse, so in particular, remember that, sorry, I'm saying words, but I should just write it down. This is the square root of lambda max A transpose A. One thing that I think is intuitive, but I'll let you check at home, is that the norm of A inverse is square root of lambda min A transpose A, like that. Which kind of makes sense, right? Because the eigenvalues, the inverse of a matrix, kind of flip order. Or this is probably 1 over, rather. Sorry. Okay, so what does that mean the condition number is of a matrix, specifically in the 2 norm? Well, it's kind of like the ratio of the largest to the smallest singular value of your matrix. Okay? Let's think about why that makes sense. I know I shouldn't have written on this board. Okay, so remember the kind of picture here, right? Our matrix like takes a circle and like maps it to some ellipse, like that. So essentially, what is the condition number? It's just like the ratio of this length to that length, like the biggest way that you stretch relative to the smallest way that you stretch. And in some sense, I feel like that's a very intuitive condition number, because essentially what it's saying is that matrices that are hard to invert are ones that involve many different scales, right? Like in some directions, scaling doesn't matter a whole lot, and then in other directions, I perturb my vector a bit, and suddenly scaling matters a lot, right? Notice, by the way, that if I multiply A by a constant, the condition number actually doesn't change. So like the fact that a matrix just contains small numbers is itself not really related to conditioning, which actually makes some sense. At least in this particular definition, where we're concerned with relative error. In absolute error, of course, that would be different. Okay. Now, so that's our basic story here. So essentially, when is a matrix hard to invert? It's when the ratio between its smallest and biggest, or I guess biggest and smallest singular values is really, really big. Think about the extreme case, right? Where basically one of the singular values kind of goes to 0 relative to the other, yeah? And in that case, notice that the matrix becomes basically not invertible. So that extreme case also kind of works out too. By the way, I should dispel one myth. Is the condition of a matrix its determinant? No, these are completely different things. So for whatever reason, people think of them as the same. That's absolutely not the case. Okay. Now, unfortunately for us, to kind of conclude today's lecture, can I actually compute the condition number? Typically not. Do you see that? That essentially, like, I need the norm of A inverse. I can't think of a reasonable algorithm for computing that doesn't involve solving a linear system somewhere, right? I mean, that would be pretty miraculous. So somehow computing the condition number is at least as hard as basically solving the system to begin with. So the condition number is largely a theoretical argument, like a theoretical object that people think about. But I think that one way to think about it is to like look at matrices and kind of guess, like, okay, so intuitively, why do we bother computing this thing? It's to kind of understand, like, if the action of a matrix on one vector scales it very differently than some other vector, then intuitively we probably shouldn't be trying to invert that matrix. Right? That's the sort of high-level takeaway of our discussion today. In fact, like I think we mentioned a lecture or two ago, I think a completely reasonable question you can ask numerically is, what is the condition number of computing the condition number of a matrix? That would make for a fun homework problem. Maybe I'll have you guys work that out at some point. It's really ugly. Or of course, it's turtles all the way down, right? Then you could ask, like, what's the condition number of that computation and so on. So instead, essentially what people usually do is they find clever bounds, right? So for example, if I know that the matrix that I'm multiplying by always takes vectors to like some lower bound on their norm, then I can like bound those singular values in different ways. If I bound my condition number below, then I know that it is at least as hard as some particular number. If I bound it above, then I know it's at most as hard, right? And this feels unreasonable, but actually there is some hope for approximation. So for example, remember we proved this bound earlier in lecture, that we can upper bound the norm of a product by the product of the norms, right? So if I kind of rearrange this expression here by dividing by x, this gives me some way to lower bound the norm of A inverse, right? So notice that actually already gives me some procedure for bounding the condition number, right? Because the hard part of the condition number is probably the norm of the inverse of the matrix. So I could substitute this bound here, and that would give me a lower bound for condition number. And in fact, for the matrix norms like the infinity norm, which are actually computable, this is enough to get pretty far. Does that make sense? So this is the kind of thing numerical software usually does. Like, it doesn't actually evaluate the condition number, but rather some other thing which we think is pretty close. And then when that thing is big, it'll still probably give you what it thinks is the solution to your problem, but it'll also yell at you and give you a warning. All right, any questions about our story? Yeah.
Wait, why does this lower bound?
Let's see here. So do you agree with the expression on the top?
Yeah.
Okay.
It still depends on
It does depend on A inverse, but at the very least, it doesn't depend on computing all the eigenvalues of A inverse anymore. Now it just involves solving a single linear system, which somehow feels a little bit more stable. You're right, though. You still have to solve this thing, which might be an ill-conditioned problem. Absolutely. Notice that even if the solution here is inaccurate, really all we care about is the length, so you might be okay. Yeah. But that's absolutely right. You see, it's actually really hard to come up with a bound that doesn't involve some calculation that's kind of against the rules. Yeah. So typically what we do in this domain is we forget the rules. Yeah. Yes. Oh, I misspoke. You're right. It doesn't flip the inequality. Sorry. Yeah. I think I did it right on the slides. I just said the wrong thing. Yeah. Okay, so I promised you guys in the last 5 minutes to compute the infinity norm of a matrix, but I'm guessing you're all bored and tired of conditioning problems. So I think maybe the better thing to do is we'll call it for now. If you look in the textbook, you'll see that there's a derivation of those two formulas that I stated early on, namely these guys, which I think are kind of nice sanity checks to see that there's just basically many different notions of length for matrices. The arguments here are really straightforward. They're basically just applications of triangle inequality. So I'll let you guys maybe read through those rather than going through them on the board and just messing up indices again. Is that okay? Okay, fabulous. So with that, we have concluded our discussion of general linear systems of equations. When we come back next time, we're going to talk about a slightly different linear algebra problem, which is to characterize the span of the columns of a matrix. So in other words, like if a matrix is no longer square, right, then the columns no longer span all of Rn, they span some subspace. And typically the thing that you want to do in linear algebra in that case is to compute an orthonormal basis, right? And so this is the first time when like the stuff you learned in college linear algebra class and what we do numerical analysis are going to diverge. In particular, there's a really famous algorithm that you probably all did by hand 400 times in college algebra class. Anybody remember what this thing's called? Yeah. Gram-Schmidt. Yeah, everybody has like terrible dreams about this thing, right? Like weird square roots appear. It's like lots of ugly numbers. And there's a reason it's so ugly, which is that Gram-Schmidt is actually a really bad idea numerically. It turns out that like Gram-Schmidt, if you think about it, right, you're like normalizing a bunch of vectors and like projecting them out, which is a great way to lead to things that are very close to zero. And so what we're going to do is we're going to start with Gram-Schmidt orthonormalization and use that to justify existence of yet another factorization of a matrix. This one's called QR, where the columns of Q are going to be an orthonormal basis for the column space of my matrix, and R is going to be upper triangular. Notice if you're like numerical analysis brain is thinking, that should be kind of predictable at this point, because what does Gram-Schmidt do? It like takes columns and it forward substitutes them to like cancel stuff out. So there's some kind of triangular structure hiding in there. So essentially we're just going to reveal that. And then we're going to say like, but it turns out numerically Gram-Schmidt is a horrible idea. Nobody should ever do this. And so there's going to be two other algorithms that you don't learn in undergrad algebra class, which is how computers do it, called Gibbons rotation and householder reflection. Fun fact, householder is somebody's name. It's not, I don't know, like some homeowner thing. So we'll talk about both of those, and then we'll return once again to the least squares problem and show that QR factorization is useful in that context. Cool, so that's a sort of peek ahead. So in any event, we're at the end of our lecture today. Everybody, please download homework 2 in 7 minutes, and then give the starter code a try. Make sure it runs on your computer. If you are in my office hours 4 hours before the deadline, panicking because you can't run the starter code, then I'm gonna send you out because I don't want to deal with that. Cool? All right. So with that, everybody have a delightful Wednesday afternoon. I'm so happy to see you all and to have made it through this upper bound without a major mistake. And I will see you on Monday.